In 1977, something very simple happened, and yet the implications of it are difficult to fully grasp unless you slow down and look at it carefully. A rocket lifted off from Earth carrying a spacecraft called Voyager, and once that spacecraft left, there was no plan to bring it back, no mechanism to retrieve it, and no realistic possibility that any human being would ever see it again. This alone already separates Voyager from most machines we build, because nearly everything humans construct is meant to be used, repaired, improved, or replaced, but Voyager was built with the understanding that it would eventually become unreachable, and once that threshold was crossed, it would continue moving without us. At the time, the objective sounded straightforward. The spacecraft would travel past the outer planets, collect data, transmit images, and extend our knowledge of the solar system. Engineers designed instruments, calculated trajectories, and relied on gravity assists to accelerate the probe outward. All of this followed familiar scientific logic. The mission had goals, timelines, and measurable outcomes. Nothing about it seemed philosophical. It was simply exploration, an extension of the same curiosity that had already sent probes to Mars and beyond. But embedded in that technical framework was a quieter decision, one that did not affect navigation, propulsion, or communication, yet completely changed the meaning of the mission. Attached to the body of each Voyager spacecraft was a gold-plated copper disc, encoded with sounds, images, and basic information about Earth. It was not necessary for the mission. It would not help the spacecraft survive longer. It would not improve data collection. From a purely engineering perspective, it served no operational function. Its presence only makes sense if you accept that Voyager was expected to outlast its usefulness, to become an object drifting through interstellar space long after it stopped transmitting. The record was designed for that phase, not for the mission itself, but for what comes after the mission ends. This introduces a subtle shift in how you interpret the launch. Instead of seeing Voyager purely as a scientific probe, you begin to see it as something closer to a long-term artifact, a manufactured object that will eventually detach from human control and continue moving independently. The moment it loses power, it does not fall, it does not burn, and it does not return. It simply keeps traveling along the trajectory determined decades earlier, preserved by vacuum, unaffected by weather, corrosion, or biological decay. The spacecraft becomes static in design but dynamic in motion, a frozen piece of late 20th century technology carried forward by inertia. When the rocket released Voyager into space, that outcome was already implicit. The spacecraft would transmit for as long as its power allowed, then gradually fall silent. And after that point, it would continue drifting indefinitely. The launch, therefore, marked not only the beginning of a scientific mission, but also the creation of an object intended to leave the sphere of human activity entirely. Unlike satellites that orbit Earth or probes that remain within reach, Voyager was sent on a trajectory that deliberately abandons the possibility of intervention. Once it departed, the timeline of the mission extended beyond operational planning and into durations that exceed human institutions. Viewed this way, the launch becomes less dramatic and more precise. A machine was built, powered, and accelerated away from Earth. It carried instruments designed to function temporarily and a message intended to persist longer than those instruments. It followed a calculated path shaped by gravity and momentum. No symbolism was required for this to be significant. The physics alone ensured that once Voyager left, it would not return, and the act of sending it outward effectively placed a human-made object into a long-term orbit within the galaxy where it would continue moving regardless of whether anyone was still listening. If Voyager were to fail because of a collision, a software error, or some dramatic mechanical breakdown, the story would feel familiar because we are used to machines ending abruptly, but that is not what is happening. Voyager is not dying suddenly. It is fading, slowly and predictably, not from damage, but from physics itself. The spacecraft are powered by radioisotope thermoelectric generators, devices that convert heat from the radioactive decay of plutonium-238 into electricity, and this process is reliable but not permanent. Each year, the fuel produces slightly less heat, which means slightly less power, and that reduction is small enough to seem insignificant in the short term, yet inevitable over decades. The decline cannot be stopped, repaired, or reversed. It is built into the nature of radioactive decay. And from the moment Voyager launched, this countdown was already in motion. As the available power decreases, engineers on Earth have had to make deliberate decisions about what the spacecraft can afford to keep alive. Instruments that once measured magnetic fields, cosmic rays, plasma density, and charged particles have been turned off one by one, not because they stopped working, but because there is no longer enough electricity to run them. Heaters that kept components warm have also been disabled, allowing internal temperatures to drop gradually. The spacecraft is being simplified over time, stripped down to only the systems necessary to maintain communication. What remains is essentially a transmitter, a power source that is slowly weakening, and a structure drifting farther away every second. The process resembles a controlled dimming rather than a failure, as if the spacecraft is gradually conserving its last remaining energy. Eventually, the power level will fall below the threshold required to operate the transmitter. When that happens, Voyager will not send a final dramatic message. There will be no announcement, no sudden silence. The signal will weaken, data rates will drop, and then the carrier tone itself will disappear into background noise. From Earth, the spacecraft will simply fade out, indistinguishable from static. This moment is often described as the end of the mission, but technically, nothing about Voyager's motion changes at all. It will continue traveling at roughly the same velocity, following the same trajectory determined decades earlier. The only difference is that we will no longer receive confirmation of its existence. At that point, the spacecraft enters a different phase. Without power, the internal electronics will cool to near the temperature of deep space. Approaching absolute zero, mechanical systems will stop experiencing thermal cycling. No motors will move. No commands will be received. The probe becomes physically inert, yet dynamically active, because inertia continues to carry it forward. In this state, Voyager is no longer an operating spacecraft in the usual sense. It becomes an isolated object moving through interstellar space, preserved by vacuum, exposed only to radiation and microscopic dust. The absence of atmosphere means there is no aerodynamic drag, no corrosion, and no conventional aging. Aside from minor surface erosion, the structure will remain largely intact for extremely long periods. This transition is subtle but important. During its operational life, Voyager functions as an extension of Earth, receiving commands and sending information back. After communication ends, that relationship disappears. The spacecraft no longer participates in human activity. It does not respond, it does not report, and it does not interact. its motion becomes independent of any human decision, the trajectory continues to evolve only under gravitational influences and its initial velocity, turning Voyager into a passive traveler rather than an active instrument. Seen from this perspective, the loss of power does not terminate the journey. It removes the last connection between the spacecraft and its origin. What remains is a silent object constructed in the late 20th century, continuing along a path through space that will persist long after the systems that monitored it have shut down. It is often said that Voyager has already left the solar system, and technically that statement sounds correct, because both spacecraft have crossed the heliopause, the boundary where the solar wind weakens and the interstellar medium begins to dominate. But this description can be misleading if you interpret it as a true escape. Crossing the heliopause does not mean leaving the sun behind in any meaningful gravitational sense. It only means that the spacecraft have moved beyond the sun's magnetic influence, not beyond its reach. Gravity extends far beyond that invisible boundary, and the region still dominated by the sun's gravitational field is vastly larger than most people imagine. In fact, the spacecraft are still deep inside the outermost structure of our stellar system, a distant reservoir of icy bodies known as the Oort Cloud. The Oort Cloud is not a disk like the asteroid belt or the Kuiper belt, but a roughly spherical distribution of comets surrounding the sun at enormous distances, extending tens of thousands of astronomical units outward. It represents the farthest known boundary of the solar system's gravitational influence, a region where objects remain loosely bound to the sun despite being separated by distances that approach those between stars. When you hear that Voyager has entered interstellar space, what that really means is that it has begun traveling through the outskirts of this immense region, not that it has escaped it. The difference matters, because leaving the Oort Cloud requires far more time than reaching the heliopause ever did. Estimates suggest that it will take Voyager roughly 300 years just to reach the inner boundary of the Oort Cloud, and after that, tens of thousands of years to cross it completely. These numbers are difficult to interpret using human timescales, because even the shorter interval extends far beyond recorded history. If you compare 300 years to the lifespan of modern science, you begin to see the mismatch, but the larger figure is even more striking. 30,000 years is longer than the entire span of human civilization, from early agriculture to the present day. During that interval, languages will evolve beyond recognition. Coastlines will shift, and entire cultural frameworks will disappear. Yet Voyager will still be moving through the same diffuse cloud of cometary debris. Despite the scale of this region, the spacecraft are extremely unlikely to collide with anything. The Oort Cloud, though massive in extent, is incredibly sparse. Objects are separated by enormous distances, and space between them is overwhelmingly empty. This means Voyager will not weave between dense clusters of comets or dodge incoming bodies. Instead, it will continue along a nearly uninterrupted trajectory, traveling at tens of thousands of miles per hour while encountering almost nothing. The motion will be steady, unchanging, and largely uneventful, defined more by duration than by interaction. The spacecraft will drift through darkness, exposed to cosmic rays and occasional impacts from microscopic dust, but otherwise preserved in near-perfect vacuum because there is no atmosphere and no significant friction. Voyager's structure will change very slowly. The metal surfaces may accumulate tiny scars from high-speed particles, and radiation will gradually alter materials at the molecular level Yet the overall form will remain recognizable for extremely long periods. The spacecraft will continue spinning slowly, maintaining the orientation set decades earlier, while its path curves gently under the gravitational influence of the sun and distant stars. In this phase, Voyager is no longer an active probe or even a silent transmitter. It becomes a passive object crossing a region so vast that its entire journey through it will outlast most imaginable human timelines. From a physical standpoint, leaving the heliopause was only a preliminary step. The true escape from the solar system requires traversing this enormous gravitational envelope, and that process unfolds over intervals that render human history comparatively brief. By the time Voyager finally exits the outer boundary of the Oort Cloud, the spacecraft will not have changed much. But everything that once defined the world that launched it will have transformed beyond recognition. Once Voyager finally moves beyond the distant reservoir of the Oort Cloud, the nature of its journey changes in a subtle but important way. Until that point, the spacecraft is still traveling within the extended gravitational influence of the sun, but beyond that boundary, its motion becomes part of the broader dynamics of the Milky Way. The spacecraft no longer belongs to a stellar system in any practical sense. It becomes one more object drifting through interstellar space, guided only by inertia and the slow gravitational pull of nearby stars. From this stage forward, encounters with other stars become inevitable, not because Voyager is aiming for them, but because both the spacecraft and the stars themselves are constantly moving through the galaxy. The first of these encounters occurs on a time scale that is already far beyond ordinary human reference, approximately 40,000 years from now. Voyager 1 will pass relatively close to a star known as Gliese 445, a red dwarf located in the constellation Camelopardalis. The term close in this context requires adjustment because even at its nearest approach, the spacecraft will still be about 6 light years away. This is an immense distance by any conventional standard, yet in galactic terms it qualifies as a near passage. The alignment does not happen because Voyager is directed toward the star. But because Gliese 445 is moving through space along its own trajectory, and over tens of thousands of years, their paths briefly converge. The encounter is therefore not a destination, but a crossing of trajectories. Two travelers passing within the same region of space without interaction. By the time this passage occurs, Voyager 1 will no longer be transmitting. Its instruments will have been silent for millennia, and the spacecraft itself will be an inert object, still moving at roughly the velocity it carried when it left the solar system. If a planetary system exists around Gliese 445, and if observers there possess sufficiently powerful telescopes, they might detect a small metallic object crossing the outskirts of their stellar neighborhood, but the spacecraft would not respond, record, or observe it. It would simply continue along its path. Unaffected by the proximity of another star, the event, though significant in trajectory calculations, would pass without acknowledgement. Voyager 2 follows a different route through the galaxy. Shaped by the gravitational assists it received during its flybys of Uranus and Neptune, its path leads below the plane of the solar system, and as a result, its first notable stellar encounter involves a different star, roughly 40,000 years in the future. Voyager 2 will pass within about 7 light years of Ross 248, another red dwarf located in the constellation Andromeda. This encounter has an additional point of interest. Because Ross 248 itself is moving toward our region of space, over time, it will temporarily become one of the closest stars to the Sun, briefly replacing Proxima Centauri in that role. During this period, Voyager 2 will be passing through the same general neighborhood, creating a moment where the spacecraft intersects the region around what will then be one of the Sun's nearest stellar neighbors. Despite the scale of these events, the physical interaction remains minimal. At distances measured in light years, gravitational effects from the passing stars will be small, and Voyager's trajectory will change only slightly. There will be no dramatic deflection, no capture, and no orbit. The spacecraft will continue onward, leaving the vicinity of each star behind. These encounters, therefore, function less as destinations and more as milestones, markers along a path that extends through interstellar space without interruption. What makes these passages notable is not the interaction itself, but the time scale involved. 40,000 years is long enough for major geological and biological changes to occur on Earth. Yet Voyager's motion over that interval remains steady and predictable. The spacecraft does not accelerate, slow down, or adapt. It continues along a trajectory determined long ago, crossing regions of space that were not even considered when it was launched. By the time Voyager 1 passes Gliese 445 and Voyager 2 approaches Ross 248, the spacecraft will simply be continuing a motion that began in the late 20th century, moving quietly through a galaxy in which stars shift positions while the probe remains unchanged. After the 40,000-year encounters, the Voyagers move into a regime where human timescales stop being useful. Up to that point, the journey can still be described using numbers that, while enormous, remain conceptually tied to civilization. Beyond that, the intervals stretch into deep time, measured not in history but in geological and stellar evolution. The spacecraft continue outward, unaffected by intention, following trajectories shaped only by gravity and momentum. And the next significant milestone does not occur for hundreds of thousands of years. During this interval, the probes experience almost nothing in the conventional sense. They do not maneuver, they do not observe, and they do not respond. They simply move through interstellar space, gradually shifting position relative to the surrounding stars as the galaxy itself evolves. Roughly 296,000 years from now, Voyager 2 approaches one of the most recognizable stars in the night sky. Sirius, unlike the faint red dwarfs encountered earlier, Sirius is a bright blue-white star, part of a binary system with a white dwarf companion and the most luminous star visible from Earth. By the time Voyager 2 passes within approximately 4 light years of this system, the probe will have been traveling longer than Homo sapiens has existed in its current form. Over such a span, Earth itself will have undergone substantial change. Ice ages will have advanced and retreated. Coastlines will have shifted, and biological evolution will have continued in unpredictable directions. Yet none of these transformations affect the spacecraft. It remains an inert structure, moving along a trajectory defined hundreds of thousands of years earlier, passing through the outskirts of another stellar neighborhood without interaction. The significance of this encounter lies less in proximity and more in duration. The passage near Sirius occurs after a period so long that the distinction between past and future becomes abstract. Voyager 2 will not record the brightness of Sirius, nor will it react to the gravitational influence of the binary system in any dramatic way. Its course may bend slightly, but the change is minor. The spacecraft does not enter orbit, does not slow, and does not alter its configuration. It continues forward, leaving the region behind just as it left previous stellar neighborhoods. The encounter becomes another point along an extended path rather than a destination. Beyond this stage, the trajectories of both Voyager probes are governed primarily by the gravitational structure of the Milky Way. The spacecraft lacked the velocity required to escape the galaxy entirely, which means they remain bound to it, following enormous orbits around the galactic center. This motion is analogous to planetary orbits, but on vastly larger scales. A single revolution around the center of the Milky Way takes roughly 225 to 250 million years, a duration often referred to as a galactic year. Over such intervals, the probes effectively become artificial comets of interstellar space, traveling through spiral arms, crossing diffuse gas clouds, and passing near stars that do not yet exist at the time of launch. During these galactic orbits, the environment remains largely empty. The density of matter in interstellar space is extremely low, so collisions remain unlikely. The spacecraft experience gradual exposure to radiation, occasional impacts from microscopic particles, and subtle gravitational perturbations from passing stars. These effects accumulate slowly, but none of them abruptly alters the probes. Instead, the Voyagers persist as long-lived objects, drifting through the galaxy while the stars themselves form, evolve, and disappear. The Sun, which once defined their origin, also follows its own orbit around the galactic center, meaning that over hundreds of millions of years, the relationship between the probes and their home star changes continuously. As time extends further, the future of the probes becomes intertwined with stellar evolution. Billions of years from now, the Sun will exhaust its hydrogen fuel and expand into a red giant, transforming the inner solar system. By that stage, the Voyagers will still be orbiting the galaxy, far removed from the region where they began. Their motion will continue, unaffected by the fate of their origin, carried forward by inertia within the gravitational field of the Milky Way. Attached to the side of each Voyager spacecraft is an object that does not contribute to navigation, propulsion, or survival. Yet it fundamentally changes how the probes are understood. It is a gold-plated copper disk, commonly referred to as the golden record, designed not as an instrument, but as a message. From an engineering standpoint, it is unnecessary, adding no operational capability and consuming mass that could have been allocated elsewhere. Yet its inclusion reflects a different kind of objective, one that extends beyond data collection. The record was intended for a time when the spacecraft would no longer function, when its transmitters had gone silent and its instruments were inactive, leaving only a physical artifact traveling through interstellar space. The disk is encoded with analog information, chosen deliberately to maximize durability and interpretability. Instructions for playback are etched onto its cover using simple scientific references, including the hyperfine transition of hydrogen as a universal unit of time. These diagrams explain how to reconstruct the signals, how to convert rotational speed, and how to decode the stored images. Also engraved is a map indicating the location of the Sun relative to 14 pulsars. Using their characteristic periods as identifying markers, this map functions as a timestamp and a coordinate system simultaneously, allowing a potential discoverer to determine both the origin of the spacecraft and the epoch in which it was launched. The design assumes no shared language, no shared culture, and no shared technological standard, relying instead on physical constants and astronomical relationships. The content of the record attempts to represent a cross-section of life on Earth. It includes natural sounds such as wind, thunter, ocean waves, and animal calls, alongside human-produced audio, ranging from spoken greetings in multiple languages to musical selections spanning different cultures. The recordings move from structured compositions to more ambient representations of human experience, including the rhythm of a heartbeat and the sound of a kiss. The intention is not to present a comprehensive encyclopedia. but to provide fragments that suggest biological diversity, cultural expresión, and technological capability. In addition to audio, the record contains images encoded as analog signals depicting human anatomy, landscapes, architecture, and everyday activities. These images are arranged to build context progressively, beginning with scientific diagrams and extending to scenes of social interaction. The durability of the golden record is determined primarily by its environment. In the vacuum of interstellar space, there is no atmosphere to cause oxidation, no moisture to degrade materials, and no biological processes to accelerate decay. The primary threats are micrometeoroids and high-energy radiation, both of which operate slowly over long time scales. Tiny particles traveling at high velocity may gradually erode the surface, acting like a form of cosmic abrasion. While radiation can alter materials at the atomic level, estimates suggest that the record could remain readable for hundreds of millions to billions of years. Depending on the cumulative effects of these processes, this longevity exceeds that of most structures on Earth, which are continuously reshaped by geological and atmospheric activity. This creates a notable contrast between the durability of the record and the environment in which it originated. Over geological time scales, plate tectonics recycles the Earth's crust, erasing surface features and redistributing continents. Mountains erode, oceans change, and atmospheric composition evolves. Human-built structures, whether digital or physical, degrade rapidly in comparison. The golden record, by contrast, travels in a region where change is minimal, preserved by isolation. The information encoded on its surface, therefore, has a reasonable probability of outlasting many of the conditions that produced it if encountered by another technological civilization. The record would appear as a carefully manufactured object accompanied by instructions rooted in physics. Its interpretation would depend on the discoverer's ability to decode analog signals and recognize the intended structure. The contents would not provide a narrative, but rather a collection of signals representing biological and cultural phenomena. In this sense, the record functions less as a direct communication and more as a time capsule. A physical archive carried by a spacecraft that no longer operates, moving through interstellar space with information preserved in material form over sufficiently long time scales, the environment that produced Voyager begins to change in ways that far exceed anything recorded in human history. Geological processes on Earth continue to reshape the surface. Continents drift, mountain ranges erode, and sediment layers accumulate, gradually removing traces of present-day civilization. Structures decay, materials recycle through tectonic activity, and even durable artifacts are eventually buried or transformed. Unlike the spacecraft, which travels through a relatively stable vacuum, Earth is a dynamic system where erosion, volcanism, and climate continuously modify the landscape. Given enough time, recognizable evidence of current societies becomes increasingly difficult to preserve, not through catastrophe, but through gradual transformation. At the same time, stellar evolution progresses. The Sun, currently in a stable phase of hydrogen fusion, will slowly increase in luminosity over billions of years. This gradual brightening alters Earth's climate, intensifying evaporation and modifying atmospheric composition. Eventually, the Sun will exhaust the hydrogen in its core and expand into a red giant, significantly increasing its radius. Models of stellar evolution indicate that during this phase, the inner solar system will undergo major changes Mercury and Venus are expected to be engulfed, and Earth's orbit may either be consumed or altered by tidal interactions and mass loss from the Sun. Regardless of the exact outcome, conditions on Earth will become incompatible with current forms of life long before these final stages occur. Oceans may evaporate, the atmosphere may thin or escape, and surface temperatures will rise beyond the range that supports complex ecosystems. During these transformations, Voyager continues its motion around the Milky Way. The spacecraft, already far from the solar system, is unaffected by the Sun's evolution except through negligible gravitational adjustments. While Earth experiences atmospheric loss and tectonic recycling, the probes remain in interstellar space, where environmental change is minimal. Their structure may accumulate microscopic damage from dust and radiation, but no large-scale process alters them dramatically. The golden record, shielded by its cover, remains physically intact. Carrying analog information encoded in metal grooves, the contrast becomes pronounced. The origin of the spacecraft undergoes fundamental change, while the artifact itself persists with relatively little modification. Over hundreds of millions of years, the Voyagers follow galactic orbits, passing through different regions of the Milky Way. Spiral arms shift, new stars form, and others end their life cycles. The probes traverse interstellar clouds, regions of varying density, and gravitational fields from passing stars. These influences gradually modify their trajectories, but the motion remains continuous. The spacecraft do not degrade rapidly, nor do they experience abrupt termination. They function as long-lived objects embedded within the galactic environment, carrying information that originated on a planet that may no longer exist in its earlier form. If a distant intelligence were to encounter one of these probes, the context of its origin might no longer be observable directly. The Sun could be in a later evolutionary phase, or the solar system might appear altered compared to its configuration at launch. The map engraved on the golden record, referencing pulsar positions, would provide a method for reconstructing the probe's point of origin in both space and time. The discoverer would see a manufactured object built with precision, containing encoded signals that represent biological forms, sounds, and cultural expressions. Even without additional context, the artifact would indicate that a technological species once existed around an ordinary star. In this sense, Voyager becomes less a spacecraft and more durable marker of human activity. Its continued motion does not depend on the survival of its creators, and its contents do not require active transmission. The probes persist as passive carriers of information, moving through the galaxy long after their operational phase has ended, over intervals measured in billions of years. Their existence contrasts with the transient nature of planetary environments, demonstrating that a small manufactured object, once released into interstellar space, can remain as a long-lived record of the civilization that produced it.